Hello everyone. We now have a lesson over triple integrals. So what a triple integral is, it's geometrically this thing. If you integrate this triple integral of 1, you're going to get volume. And you might ask, why would we go into this when we already have something that can compute volume from like the previous lecture? If you were to compute, you have some function double integral f of xy dA that gives the volume over some region of the function f. But if you were to compute the double integral of the number 1, you pick up what is the area. Okay, so what this is really actually used for, not so much is to compute the volume, unless you have something really complicated to compute the volume of, which we're going to get to at the end, which we will eventually need to do it. But what it really is if you were to integrate a triple integral of a function. Now, f of x, y, z, so it's going to be an iterated integral, and just for example, I'm just going to write it as dz dy dx. But you can flip these orders of integrations provided it's continuous using that Fubini's theorem, which your functions will be, but whatever. So now, this one here had dy dx. You have dz involved here. So this is actually a function which has inputs from R3 and outputs into R. So this is actually a higher dimensional function than that one right there that you previously messed with. So what this is actually used for is computing density in like fluid mechanics or anything like that, or some kind of like something with the air. So if you need to compute the density of something that has like it varies in like sort of like viscous nature, so something like some kind of fluid. So you'll see this in your physics courses where it's really going to pop up, like for computing mass and density. So that's what it is. And so look, before we get into like more technical ones, let's just try to compute one of these. So it works the exact same way as a double integral. So this one's already set up, iterated to do dz, dy, and dx. And so z goes from 0 to 4, y goes from 0 to 2, and x goes from 0 to 1. So this is just going to be a box. All right, like just to give you a heads up before we start like messing with anything more difficult. So you just do it in order. So I leave the outer integration alone. All right, now when I integrate this inner function here, x times y times z, with respect to z, x and y are constants. So x times y multiplied by the antiderivative of z, which is z squared over 2, and you evaluate that from 0 to 4, and then eventually continue with the integration. Okay, now I leave, when I'm going to plug this in here, this is going to turn into 4 squared divided by 2 minus 0 squared divided by 2. The later limit is 0. The other one would be 16 by 2, so that's 8. So that's a constant. I'm going to move that out to the front. 8. Now I have the integral 0 to 1, 0 to 2 of x times y dy dx. Now we're in a position like just like from the previous homework. So x is a constant, antiderivative of y is y squared over 2. So I have 8 times 0 to 1. X was a constant, y squared over 2. That needs to be evaluated from 0 to 2. And then eventually I have to deal with the differential dx. Alright, so this is, so when I plug in the number 2, that's about to be 4. 4 divided by 2 is 2. So then this whole thing, so I have 4 divided by 2, which is 2. Let me put it with the 8 as a 16 out front. And the limit of integration at 0 is 0. 0 to 1 x dx. Now I just go after it. That's the antiderivative, which is also x squared over 2. Upon evaluation, antiderivatives x squared over 2 needs to be evaluated from 0 to 1. You're going to end up with 1/2. So 1/2 on the 16, and you'll get to 8. All right, let's look at a more complicated one. I want to scoot this in for the limits of integration here. So fortunately, I could see it's a little blurry. Now this is a way more complicated situation. So Z is going between a function which is 0 and y. Y is going between these two functions, x and 2x. And x is going between 0 and 1. Okay, so we do the integration the same way, just go after one after another. But the domain of integration is something way more technical. And whether or not we want to get into like trying to draw it, I wouldn't really suggest it unless you need to do that. So let's just compute it, like just go for it as is, just using like properties of math. So you'd have inner integration with respect to, so all the antiderivatives are the same. But you have to, but notice how these are functions, and you could have actually, since all these were split up as numbers and all these are constants, split this thing into 3 separate integrals, so that like it might have made the computation easier. But like I wanted to go through it like in this iterated process, because if these are all set with functions in them and the inner ones, you have to go through it in the iterated process. So first I leave the outer two integrals alone, 0 to 1, x to 2x. Alright, the inner which antiderivative x and y are constants, need to multiply that by z squared over 2. Evaluate that from 0 to y. Then I have dy dx I'll have to deal with. Maybe I'll put it right here underneath it. Alright, now so when I evaluate using the fundamental theorem of calculus, this will be y squared by 2 minus 0 squared over 2. It's just going to be y squared, and then I'll put the 1/2 out front. 0 to 1, x to 2x, x times y cubed. There's a y there and a y squared there. And then dy dx. Alright, so now I have 1/2 in front, 0 to 1. X was a constant in this when I'm dealing with different integrating with respect to y. Then that's going to be y to the 4th over 4. Let me scoot this under the computer just in case the microphone's recording. Okay, so then antiderivative is y to the 4th over 4. So alright, then that has to be evaluated between x and 2x. And at the end you have to deal with the differential dx. Alright, now, alright, let me put the 4 with the 2 out in front. So 1/4 and 1/2 come together as 1/8. Alright, now, the integral is now 0 to 1. You're about to have 2x to the 4th. So I have x sitting here, 2x to the 4th minus x to the 4th. All right, dx. Now we're just at a Calc 1 integral. Just going a little further, 1/8. All right, so then now this you have 2 to the 4th. That's 16. All right, then you're going to have x to the 4th, and with an x to the, you'll have here x to the 5th. All right, then you will need to multiply, so you have x to the 5th, or we could just actually we could just tally this whole thing up as is. So like right here you have 16, because 2 to the 4th, then you're taking off 1, so you're about to have 15 worth of these objects in here. So 15, this is going to be x to the 5th. Antiderivative is x to the 6th divided by 6, so that when after I've evaluated from 0 to 1, I would have just a 1/6 coming out of this integration. So then that would be your end answer on that. Okay, let's look at a little more complicated one here. So let me scoot this down here. Alright, now, okay, so this function here, it also has limits that have functions in them. So you can see it goes from 0 to, z goes from 0 to x goes from 0 to y, and then y goes from 0 to 1/2. So it usually works that like you have the functions here, and on the very last one it's going to be numbers. So you can't have the one on the last one having any kind of functions on it. The inner two ones are the ones that have the functions as limits of integration. Okay, so that's just something to note here, like when you're learning how to set these things up. Okay, so here, so when you're doing this, you want to think like doing a chain rule on this function here, and it's going to have to happen multiple times on this, and this one's going to get a little long and messy at some points. But like, let's just get through the integration for z first. Okay, so this is your function. So the antiderivative of sine of x plus y plus z with respect to z, the antiderivative is, let me write out the outer integrals. Okay, antiderivative of, so doing a chain rule, it would be negative cosine of x plus y plus z, and that needs to be evaluated from 0 to x. Then you have to do dx and then dy. So that's using a chain rule like via Calc 1 method. So, and it's just do u substitution and you got to put it back in. Okay, now let me value that z goes from x to 0. So then this integral is 0, or I'm sorry, the integral is 0 to pi over 2, integral 0 to y. The function now you must integrate, it will be negative cosine. When you put x inside here, it's going to be, there's another x there, 2x plus y minus, so now doing the fundamental theorem, minus, and then you'd have another double negative plus cosine of x plus y. Alright, now we're at a situation where we're like doing an integral from the previous lecture. So now continuing on, okay, so leaving the outer integration alone, 0 to pi over 2. Alright, so I'm doing, now I need to differentiate with respect to x. Alright, antiderivative of this function here is going to be negative sine of 2x plus y, and then doing a chain rule, divided by 2. Antiderivative of this one is going to be plus cosine of x plus y. Then you're going to have to evaluate this whole thing here between 0 and y, dy. Alright, I'm sorry, and that should be sine. I don't know why I wrote cosine there. Okay, now you just plug in the limits of integration with respect to y. Okay, so now let me just clean this up. 0 to pi over 2. Yeah, this is going to get barely even fit on this thing right here. So, okay, when you put in and you're plugging, when x is y, all right. Okay, so you're going to have negative sine of, so I'm putting y in there. That's going to be 2 y's and another y, 3y. I have it divided by 2 plus sine of 2y. So that's for the upper limit of integration. Now you have to do, from the fundamental theorem of calculus, plugging in the lower limit, and it would be, formally it would be minus all of this. And so taking that into account, a double negative on the first one would be sine of, so when x is equal to 0, sine of y over 2. That negative would have come through from distributing on the fundamental theorem of calculus on that plus sign, and then sine of y. And then you have to integrate that thing with respect to y. If you want for practice, when you work this thing out, you're going to get 1/3 to complete this problem off. But like at this point, it's just now super basic Calc 1 integral. So that's the technique of what's going to get used out of all this. And so that's just some warm-up examples. The next in the notes, I have this page here. Now this page, all I want to do is just discuss it in light detail, because it's way more, like, this is the formal definition of what's going on and how these things are set up. And big picture is all it's talking about is how these orders would be different, like whether it's going to be dz, dy, dx, or situations where like it would be down below. Let's see where they at. Like say, and having like dx come first and all this. All right, all this is talking about is different ways you enter into the function to set up the limits of integration, and that's going to be what the whole game is going to be about. So I figure, like, let's just jump into the problems and not mess with all this technical stuff like type 1, type 2, and type 3. But if you want them, here they are. I think we should just work the problems and see how far, like, deal with problems as they come along. Okay, so evaluate this triple integral where E is the solid that lies under this plane and above the region in the xy plane bounded by the curves y equals square root of x, y equals 0, and x equals 1. Okay, so given they basically told you how to set this thing up like almost to the T, but there is like one little issue. So we know that like if we just like say just start writing down what we think would happen. Okay, and it says and it wants me to get the like d, so the function would be 12 times xy. It told me that z goes between it goes like it's under this plane and above the xy plane. So z goes from 0, that's the xy plane, up to 1 plus x plus y. Then it tells me something about y. It says y is bounded between square root of x and 0. Okay, so then that tells me that it's got to go like this. Now it just says and x equals 1. So what are the like 1 is definitely going to be involved on this, but what is the other limit of integration? So for that, like let's go to a picture and figure out like what is this. So a projection onto the xy plane. That's y equals square root of x. The function y equals 0 is this one. And that thing saying x equals 1 is corresponding to that line. So that the domain on the projected down to the xy plane, that's what you're looking at. And so since it said y went from 0, y came in like this. The direction of y entered at 0, exited at square root of x. And then since x, they said to do it up to 1, given that this is the picture, x had to go between 0 and 1. 0 and 1. And then that would be your triple integral you have to evaluate. And at this point, it would be exactly the same as the first 3 examples. You just have to go through it. You're going to put dx on the back. So antiderivative with respect to z of this function. So there is no z in there. Like maybe let me just set up what the antiderivative with respect to z is. So you basically be treating this as like a constant. So the first which integral is going to be, you'd have 12 times x times y. Now formally, like writing it in, eventually you would do this fast, but like the antiderivative of 1 is z, so between 0, 1 plus x plus y. So that now this triple integral is 0 to 1, 0 to square root of x, 12 times x times y, times 1 plus x plus y dy dx. That's using the fundamental theorem calculus on this little polynomial on z and evaluate it at 0 being 0. Then you would distribute this in on each of these members and then integrate with respect to y, keep going, and then go for x like we did on the first ones. Alright, let's look at another one here. Alright, now this one doesn't give you much information here. It just gives you enough to set the thing up geometrically, and then once that's done, then you have to do the integration. Okay, so triple integral to find the volume of a tetrahedron enclosed by the coordinate planes and this plane here. So let's try to draw this and figure out what are these limits of integration have to be. So xy, this is the all of R3, x, y, and z. Okay, so first, what does this plane look like, and how can I set these limits up? Okay, what happens when x and y are 0? So basically I want to know, like, where does this thing touch this z-axis? When x and y are 0, so that would be 0, that would be 0, z is equal to 4. So let me put that point on there. So that's run 0, walk out that way 0, you will be rising 4. Now, what happens when y and z are equal to 0? So that would be, what point does this thing touch on this axis? When y and z are 0, you have 2x equals 4. So then x, it has to be 2. So this would be 2, 0, 0. Now if x was 0 and z was 0, so that would be on this line here, you'd see that y has to be 4. Okay, so x was 0, y was 4, and z was 0. So this tetrahedron is this thing right here. And for the back walls, it has that plane and that plane on the back. And then you have the lower one here. Okay, so now how to set this up. So I would probably suggest setting this up. So like you'd want to set this up so that, like, I would do the integration with respect to z first, since I could solve this function out with respect to z pretty easily. And then, so if I solve this out with respect to z, you end up with z equals 4 minus 2x minus y. Z enters. So now in the direction of z, I'm coming up. Boom. I enter at z equals 0. I exit on this face of this tetrahedron. So then that means the triple integral gets set up. Okay, so, and I'm doing volume, so I need to integrate 1. Alright, dz. So coming in, like, you want to think like I hit that bottom plane right there. I will pop out the side of this tetrahedron, this face that we're looking at. So enter, and then exit. Now it doesn't matter which one I do next, like whether it's dy or dz or dx, sorry. But I still need to figure out what these things have to be. Alright, so now, like, let's think about what does it look like on the ground. Alright, on the ground, if we were to do projection onto the xy plane, alright, this thing says it's a line and it goes through 2, 0, and then also up through 0, 4. So that's what that looks like on the ground. If I want to integrate with respect to y first, I'd be coming in like this. Enter at 0, exit at this line here. So guaranteed enter at 0, exit at that line. Alright, that line you can figure out from like college algebra. It has slope -2. So that line is represented by -2x plus its intercept, sorry, which is 4. So you exit, enter at 0, exit on that line. -2x plus 4. -2x plus 4 is what y goes in between. And then from this picture, you can see x roams from 0 out to 2. So the triple integral is z went between the 0 and that plane because you were coming in from the bottom and you shot out the face. Then to figure out what the limits of integration for y and x were, we went to a projection onto the ground. When we project onto the ground, you will, if you want to choose y, you will come in, enter at 0, y equals 0, exit on that line. So that you're looking at that, and then x went from 0 to 2. So that is one way. And if you wanted to do the other way, x coming in first, that's okay. And if you want to start switching this around, you can, and that's what the last problem's about. But I would suggest just try to set it up the way that's the easiest, and that will be what you're looking for. All right, let's look at the last one here. All right. Now this one, what this is all about is just like messing with switching the orders of integration. All right, and then that is that can get real messy real fast. And so and it only wants me to do two other different orders. All right. And like it said, there's a total of 6 different ways you can do this. All right, so let's think about which one we want to do first. Let's see. So maybe the easiest one to do is to leave Z alone and mess with X and Y. All right, so if I leave Z alone and mess with X and Y, it's like just one. So method one of these. So for one. And on all of them, you'd want to so I'm going to leave Z alone, and I want to do X and Y. Okay, so now if I'm doing X and Y, when I look at the projection onto the X-axis, into the XY plane, you have that square root function. All right, and then it's bounded up here by 1. So it looks like that down there. This thing it's set up originally like enter right there, exit right there. So that's how it's set up as is. If I want to switch it going the other way, so I would have the triple integral. I'm not messing with Z. That's where it gets more difficult. Alright, so say I want to enter with respect to X. Enter in the direction of X is come in like this. Enter, exit. I will enter on X equals 0. Sorry, Z goes first. Sorry. Right there's Z. dx. Enter on 0. Exit right there as a function of X. So solving that out, that would be Y squared. Then Y runs from 0 up to here, which would then be corresponding to that Y point. But if that was 1, that has to be 1 also. So 0 to 1. All right, let's do another one now. So now let's really start switching, get Z out of the picture here. Okay, so let's go for another method here. Okay, so another way to approach this thing. Okay, so what I want to do is think about coming in the direction of X first. So what does that mean, coming in the direction of X first? All right, let's see here. So what I mean is I want to have this dx enter as a function of X. Okay, so that would be coming in like this onto this surface. All right, and so as soon as you're coming in on the back, you're going to hit that back wall. All right, you would hit the back wall. So you enter in at 0. So then coming in on the back wall, then what are you going to, you will be in this function. You will be coming out of this side right here. All right, so then now you're coming out of that side. So that side would be represented by Y squared. So coming out of that. Then I would have, at that point, I have to figure out what are the limits of how do I set it up for whatever I want to do, whether dy or dz or dz dy, whatever. I'll just write this one for now. Okay, so imagine here's y, here's z. So now I'm projecting onto the yz plane, so that's the back wall. All right. So on the back wall, what you're looking at is z as a function of y is 1 minus y. So it's another situation. Sorry, I didn't notice the camera wasn't on there. This is going to be on that back wall. You have some kind of line. Right here is so that's the function z equals 1 minus y. Y-intercept is 1. Negative 1 is the slope. Okay, so then that has to be 1 also too. So if I want to come in with the direction, and in fact, and as I have this set up, you know what, I'm going to put z here and then y. Direction of z is coming in like this. Boom, enter, and then exit on that line. So I enter on 0, I exit on 1 minus y. for the direction of y. So how long do you do this? Between 0 and 1. And so that's the needed 2 orders that they want me to calculate on this. So I would say just when you're setting these up, just try to draw like usually the first limit, the first entry, whether it's z or x on this one, comes from like what you're looking at geometrically. How would it have entered into this picture here? For example, if I want to enter into this with respect to y, like you think like you're like a little like an ant walking, and then it hits, bam, it hits on that face. Where's it going to exit? On that face. So if I was going to do like, maybe let me just set it up like the outside part. So imagine I want that one to come first, dy, and then who knows what I want to do after that. You will enter on that face, square root of x. You will exit on that back face, 1 minus y. And then at that point, then I'd have to go to drawing a picture, which I'd have like a z and an x here, and then I would try to like graph the function, like what does this function look like projected onto the xz plane, and then set these up just like before. So that's the end of everything, and hope everybody has a good day. Thank you very much.